Welcome to your AP Statistics lesson on Chapter 24, Comparing Means. This is Mrs. Brown, and I'm here with my trusty pups, Daisy and Scout, and we are ready to talk statistics. So comparing two means is not that much different than comparing two proportions, but this time our parameter of interest is the difference between the two population means mu1 minus mu2. Remember that for independent random quantity, variances add. So the standard deviation of the sampling distribution of the difference between two sample means is going to equal the square root of the sum of the variance of the sampling distribution of each of those sample means. So we still don't know the true standard deviations of the two groups, so we're going to need to estimate using the standard deviation of the two samples that we have, and so we will use this standard error for our sampling distribution of the difference of sample means. Because we're working with means and estimating the standard error of their difference using the data, we shouldn't be surprised if the sampling model is student's t. The confidence interval we build is called a two-sample t interval for the difference in means, and the corresponding hypothesis test is called a two-sample t-test. Okay, when the conditions are met, the standardized sample difference between the two means of the independent groups is t equals our estimate minus the parameter divided by the standard error of the estimate. It can be modeled by students' T model with a number of degrees of freedom found from a special formula we'll talk about in just a minute. And again, I have a reminder here of what our standard error formula is. All right, we have a picture here at the bottom of kind of what's going on, just so you can conceptualize what you're seeing. We start off with two populations, population 1 and population 2. Population 1 has individual values, individual x's, if you will, that are centered around a true population mean mu1, and population 2 has this similar construct with observation centered around mu2. Then we start taking samples of size N1 and N2, and we start finding sample means and develop our sampling distribution of the sample means. So here's our sampling distribution of sample mean 1, still centered around mu1, and here's our sampling distribution of sample mean 2, still centered around mu2. When you subtract a random variable from the other, the mean of that difference is going to be the difference of the true means. And so our sampling distribution of the difference in sample means is going to be centered around the difference in population means. And then the standard error is given up here by this nice formula. Okay. There are assumptions and conditions. Some are about each individual group, and then there's one about the two groups taken into consideration together. So when we say independence assumption here at the beginning, this applies to both groups, and so you need to check these conditions for both groups. Luckily, we really typically only check one of them, which is the randomization condition. Were the data collected with suitable randomization, representative random samples, or randomized experiment? And you have to check that for both samples. All right, the 10% condition, if we had to check it, we would check it for both groups, but we usually don't check this condition for differences of means. We will check it for means only if we have a very small population or an extremely large sample. Now, the nearly normal condition does need to be checked for both groups. A violation by either one violates this condition. So you hope you either have information that the original populations are normal or that your sample sizes are at least 35 each, and then you can appeal to the CLT. If you have data and you have less than 35 observations, you need to enter them into your calculator and do a histogram, show a histogram or a dot plot or stem plot, something, or normal probability plot, something that shows that both groups aren't too far off from normal. Okay, so those are the assumptions and conditions the assumptions we have to make and conditions we have to check about both groups. Now we need to consider the relationship of one group to the other group, and this is the independent groups assumption. The two groups we are comparing must be independent of each other. There is actually a set of methods that we're going to look at in chapter 25 if we have groups that are not independent of each other. We didn't have an analogous um, inference method for proportions, so it's going to be kind of a little bit of a new thing for means, but we'll worry about that in the next video. All right, when the sample conditions are met, we are ready to find the confidence interval for the difference between means of two independent groups, mu1 minus mu2. And so you can see our confidence interval follows our general pattern. We've got our estimate, the difference between the sample means, plus or minus the critical t-value based on our degrees of freedom, which we're going to get to. And this is multiplied by the standard error of the sampling distribution of the difference in sample means. And we've got a reminder here of what the formula is for that standard error. The critical value, of course, depends on the confidence level, C, and the number of degrees of freedom, which we'll get from the sample sizes in a special formula. All right, so here's that special formula, and it's really special. And by special, I mean complicated. Luckily for us, technology does that for us instantaneously and without any calculation errors, so we will let our CASs do their magic for us. All right, so and the other type of inference we do is hypothesis testing. So when we test our hypothesis, when we're doing hypothesis testing, our null is going to be that the difference between the means is 0, or that mu1 equals mu2. Logically, those are the same things. So for this, our test statistic looks a little less complicated than it did for confidence intervals, because under our null, the difference between the population means is 0. So we don't have to write the minus 0 in the numerator there, so it looks a little cleaner. We have the same standard error. When the conditions are met and the null hypothesis is true, this statistic can be closely modeled by a student's t-model with a number of degrees of freedom given by that special formula we just saw, and we use that model to obtain a p-value. All right, so it's going to ask about pooling. We don't care if, there's T in the pool. We don't need to test anything. We only care if there's P in the pool. So we only pool for to proportion problems. We never pool when we're working with means. All right, let's look at some examples. Stereograms appear to be composed entirely of random dots. However, they contain separate images that a viewer can fuse into a 3D image by staring at the dots while defocusing their eyes. An experiment was performed to determine whether knowledge of the form of the embedded image affected the time required for the subjects to fuse the images. One group of subjects, group NV, received no information or just verbal information about the shape of the embedded object. A second group, VV, received both verbal information and visual information, specifically a drawing of the object. The experimenters measured how many seconds it took for the subject to report that he or she saw the 3D image. And so a 90% confidence level was used, and there are 70 degrees of freedom, and we end up with a confidence interval of 0.55 and 5.47. We're going to interpret our interval in the context. So hopefully by now you kind of know the general pattern for this, but let's look at the phrasing when it's a difference in means and in this particular context. We are 90% confident based on this sample or these samples that people who receive no or only verbal information about the image in a stereogram will take between 0.55 and 5.47 seconds longer on average to report they saw the image than people who receive both verbal and visual information. Does it appear that viewing a picture of the image can help people see the 3D image in a stereogram? Yes, since the whole interval is positive. Remember, if 0 is in the interval, since we're testing against the null, that the difference in the means is 0, if 0 is in that interval, our interval would not give us evidence that viewing a picture helps people. Our evidence would be consistent with the null. But our whole image is positive, 0 is not in there. So yes, if we were stating this more formally, we have significant evidence that there is a difference in the average time, the true average time it takes for people to recognize the object if they are given verbal and visual information. All right, last example, and we're just going to look at part A. In an investigation of environmental causes of disease, data were collected on the annual mortality rate, deaths per 100,000, for males in 61 large towns in England and Wales. In addition, the water hardness was recorded as the calcium concentration in parts per million, ppm, in the drinking water. The data set also notes for each town whether it is south or north of Derby. Is there a significant difference in mortality rates in the two regions? Here are the summary statistics. All right, we're going to test appropriate hypotheses and state our conclusion. So our null, before we get to that, let's go ahead and check our conditions and make sure we can do a test. It is plausible that the water supplies of towns in the samples are representative of all water supplies north of Derby and south of Derby. The samples seem to be independent of each other. The sample sizes are large enough that if the distributions are unimodal and reasonably symmetric, the central limit theorem should apply. So we've got 34 from the north, so that's good. It's greater than 30. 27 isn't greater than 30, so it's close. It would be better if we were told that the individual concentrations were normally distributed, or if we had a list of the data so we could show the distribution. We can't, so we're going to put a little caution statement there. We will proceed with caution as we conduct a two-sample t-test. Okay, so we're going to be diligent in writing our hypotheses and explicitly stating what our parameters are so that we get full credit. Our null is that mu of north is equal to mu of south. That's just another way of saying that the difference is equal to 0. Those are logically equivalent. And so where mu n is the true mean calcium concentration for towns north of Derby, and mu s is the same thing for towns south of Derby. Since it asks about is there a significant difference in mortality rates, we're doing a two-sided test. So our alternative is not equals to. If you wanted to write it as a mu n minus mu s is not equal to 0, that would be the logical equivalent. So we let the calculator do its magic, and we get t equals 6.47 using that complicated formula, which the calculator does for us. We get degrees of freedom of 53.49. And we get a p-value of 3.2 times 10 to the negative 8, which is essentially 0. I wrote it out there because sometimes people want to report the p-value as 3.2. It can't be 3.2 because it's a probability. So anytime you have a number there, that's larger than 1, look, and it is going to be multiplied by 10 to some negative power. And when you consider the whole of the number there, it's close to 0. Due to our small p-value, approximately 0, we reject the null. There is sufficient evidence to support a difference in the true mean calcium concentration for towns north of Derby and towns south of Derby. Okay, that's it. Thank you so much for watching the video. Try the problem to try on your own, and we'll go over them in class and get started on our classwork. Thank you, guys. Have a great day.